Okay, so today we're focusing on related rates. So you can turn to page 9. Now, if you remember with implicit differentiation, we had to do something a little different with y variables, right? We had to attach that dy over dx as soon as we took y's derivative. With related rates, it's kind of the same idea, but now every variable is getting impacted with something additional. It's not just the y's, it's the x's, it's the y's, it's the r's, it's the s's. Every variable gets impacted by time. But it's the same process, just like how with implicit we would do, if it was y squared, we'd do 2y dy dx. But now it's going to be 2y dy dt. Everything's going to get impacted by time. So here are the steps, and these steps are not going to be in any particular order. It's just we have to take care of these. Identify the equation that relates to variables. Sometimes it's Pythagorean theorem. Sometimes it's surface area, which could be a trig equation. Sometimes we have similar triangles involving cones, or similar triangles like cones or shadow problems. And then we find the derivative with respect to time of that equation. And every variable is going to have a time component to it. And then we have to solve for the variable in the new derivative equation. Okay, so the very first related rates problem that we did was a ladder problem, where we have a ladder kind of leaning against the wall. So let's start off with that problem. So we have a 15-foot ladder sliding down a building wall at a constant rate of 2 feet per minute. How fast is the base of the ladder moving away from the ladder when the base of the ladder is 9 feet from the building? So here's my diagram. So this is the motion that the ladder is going to undergo here. It's going to slide away from the wall and it's going to slide down. But we're really thinking about how this is affecting the length of the triangle that's formed by the wall, the ground, and the ladder. So I'm going to start off with x, y, and z being my variables there. We know that the equation that's going to relate the 3 variables is Pythagorean theorem. So we can say x squared plus y squared equals z squared. We apply a derivative rule for every variable, but then we have to immediately attach a d over dt for that variable. So x squared becomes what? What's x squared's derivative? 2x. But we're getting impacted by time, so multiplied by what? Dx over dt, yeah. So every variable is going to have a d over dt for that variable, okay? Plus y squared becomes 2y dy dt. And then z squared to z, and then dz dt. So x, y, and z represents the length of the sides of the triangle at any moment in time. But dx dt, dy dt, dz dt, these represents how fast that length is changing as time passes. So what do you expect out of dx dt? Do you expect dx dt to be positive or negative? Positive. Because why? Yeah, because its value is increasing. Not because of the direction, right? We don't want to ever make our decision for signs based off of the direction. We don't want to assume, oh, left is negative or right is positive. Think about what's happening to that value. You do have to kind of imagine what's, how the shape is changing, and use that to help you decide whether you want your rate to be positive or negative. So x is growing, so we want dx dt. So we know ultimately dx dt will be positive. What do you expect out of dy dt? Negative, not because it's going down, but because we expect this value to be shrinking as time passes. What do you expect out of dz dt? Okay. The ladder is 15 foot at the beginning of the problem, 15 feet at the beginning of the problem. What's the length at the end of the problem? Still 15. So what do you expect out of dc dt? 0. Yeah, it doesn't change, right? As time passes, it's going to remain statically 10. Not every problem is going to have hypotenuse being a rate of 0. It depends on the problem. If I have two planes that are um, um, uh, uh, flying away from the same location, that hypotenuse is going to be growing over time. Everything is growing over time, but it depends on the context of the problem. Okay, so we like to list out all of our variables. Okay, 15-foot ladder is sliding down the building, so we can assign 15 to be the at a constant rate of 2 feet per minute. Anytime you see a time component, you know it's going to be one of the rates. Okay, so sliding down a building at a constant rate of 2 feet per minute. What do you think we can assign this to be? dy dt, yep. And then what adjustment would you make? Negative, right? Okay. How fast is the base of the ladder moving? You see the word base, that's referring to that horizontal component of our triangle. How fast is it moving? That's the unknown. That's our dx dt. When the ladder is 9 feet from the building. So when the base of the ladder is 9 feet, so we know that's x. Okay, we know what dx dc dt is, right? We already talked about how the ladder is not changing over time, so the rate of change is 0. And if we had 5 out of the 6, we can plug in, but how can we find y? Diagonal theorem, yeah, you know that at this moment in time, if I have two sides of a right triangle, I can find the third right triangle. This is basically a variation of a 3, 4, 5 right triangle. So you can use your calculator. You can also see that, a multiple of 3, 4, 5 would be 9, 12, and 15, but you just plug in to x, z to solve for y. Okay, so now everything should be ready. Replace all your x's and y's and z's with our value, and then use our calculator, and we can solve for dx dt. All right, try that. we expect dx to be positive. It should come out to be a positive value. And if you're struggling with what the units should be, look at your variable. Your variable is going to tell you what's involved. X is in terms of feet, T is in terms of minutes. So you put them over each other, feet per minute. All right, next up, we have speech ball. V equals 4/3 pi r cubed, S equals 4 pi r squared. We're going to be involving their derivatives there. So find the rate of change of the surface area. Let's build out both of the derivatives. We know that we're going to need both of them potentially. So V is equal to 4/3 pi r cubed. Notice that pi is just a coefficient. It's not going to impact our derivative much. It's really just V and R that we have to find the derivative for. V's derivative is just 1 dv dt. Four-thirds pi is a coefficient. That's not going to go. That's not going to go anywhere. It's the r cubed that's getting power rule. So r cubed becomes 3r squared multiplied by what? dr dt. Okay. Let me just do a little bit of cleanup. dv dt is equal to 3's cancel out. I'm left with 4 pi r squared dr dt. What is the rate of change of the surface area? I know ultimately I need to build that ds dt. Let me just get that out of the way. So S's derivative is 1, but time is involved. So 1 times ds dt. 4 pi r squared. The 4 pi is not going to go anywhere. It's the r that's getting impacted. So times 2r dr dt. So everything that we need calculus-wise is in front of us. If we need the v, we have it. If we have a surface area equation, we can use it. If we need it, we have a dv dt, we have a ds dt. We may not need everything, but every formula that we need is in front of us. Okay, so I like to do that first, get that out of the way, and then let me just start collecting information here. A beach ball is deflating at a constant rate of 10 cubic centimeters per second. What variable is this referring to? dv dt. The way that you can tell is you see cubic centimeters, you know it's got to be something volume related, and you see seconds, so it's got to be time related. So the only variable that has both those things together is dv over dt. Anything special about dv over dt? Negative, because it's deflating, right? That volume is decreasing as time passes. So we do want a negative 10 for dv dt. When the volume of the ball is 256 over 3 pi cubic centimeters, what can we assign that to? That's just what? Just V, right? We don't, just cubic centimeters, no time components, so just V. What is the rate of change of the surface area? So we're looking for ds dt. So it's a bit of a puzzle here because we just have to kind of fill in the different, we may have to find a set of information before we can find the next one. But let's start from the end here. At the end, we know that we're trying to get to ds dt, and we need r, and we need dr dt, which we don't have right now. So we don't have r, but is there a way for us to get to r? What can we use to help us get to the value of radius? Will one of these values help us out? Let's think. You see a way for us to get to the value of the radius using one of the equations that's available to us. Yep. Good. So we have the volume value or volume value. We can plug that in, replace that for V, and then that should be able to help us isolate R. And if we have R, then that will get us closer. So we can use this and this to solve for R. Okay. What could we use to get to dr dt? Okay. Maybe this dv dt can help us, right? Because if we have our dv dt value, and assuming that we have our r variable found, we can use that to solve for dr dt. Let me highlight that orange here. We have dv dt is -10. We can use that to solve for dr dt. But let's focus on solving for r first, right? We have our volume value. We should be able to algebraically solve for r, and that will give us that first piece that we need for this problem. Okay, try that. Solve for r first. What I highlighted in pink here. Okay, if you're coming in just now, we're on page 9 of packet 2. Mm-hmm. I can divide both sides by pi, that goes away. Divide both sides by 1/3, that goes away. So we should be able to clean this up. (256) equals 4r cubed. Divide both sides by 4. I get r cubed equals 64. So r is equal to 4. Okay. Next up, I can use that information to solve for dr dt, because we need that dr dt as well, right, to ultimately have enough information to solve for ds dt. So dv dt gets replaced with -10, r gets replaced with 4, and then we can solve for drdt. Uh, 4 squared times 4 is 64. Divide both sides by 64. I get negative 10 over 64 pi. Now notice that we're also dividing by pi, so that pi has got to stay in the denominator. We can't just let it float up to the top. It needs to stay below. Okay, our final step, insert all of that into our dsdt. We have our radius. We have our drdt. Should be able to put it all together, put it in and solve for dsdt. 8 pi times 4 times negative 5 over 32 pi. A lot of things cancel out. 8 times 4 is 32. 32 divided by 32 is 1. Pi divided by pi is also 1. So we're left with negative 5. And what's our unit of measure going to be? Surface area over time. Surface area, what's our unit for surface area? Let's focus on that word area, right? Surface area. Is it centimeters? Squared, yeah. Centimeters squared per second, yeah. And it should make sense that we're getting a negative, right? If the volume is shrinking, you expect that surface area to also be shrinking as well. So that negative should come out naturally, and it does. The most labor-intensive related rates problems are these cone problems where we have to do similar triangles and then get our variable down to either radius or height, and then find the derivative and then plug everything in. Okay, so water is being poured into a cone container. The cone points directly down and has a height of 30 centimeters and a base radius of 10. How fast is the water level rising when the water is 4 centimeters deep? We know that the container dimension is going to stay at a constant 10 and 30. However, the dimensions of the water or the water inside the tank is also forming its own cone shape, but those are ever changing, right? So I'm going to we use R and H to indicate that, you know, as the water is poured in, that radius is going to keep growing and the height is also going to keep growing. But we're just going to look at a portion of this diagram so we can kind of see that similar triangle component. So I like to start off by building that similar triangle relationship. We can say the radius of the small cone is to the radius of the large cone, as the height of the small cone is to the height of the large cone. I'm going to cross multiply here. And I do have to make a decision in terms of which variable do I want to solve for, which variable do I want to keep, which variable do I want to remove. And the rest of the problem should give us that hint. How fast is the water level rising? We're looking for the HDT. When the water is 4 centimeters deep, they also give us information about the height. So these are nice clues to indicate, okay, if we can have our volume equation in terms of height, then these will just naturally show it for us, rather than radius. I mean, we can still get to this from radius, but it'll take, maybe another step to get to it. So we can move a little bit quicker if we can kind of see, how is this information going to help us down the road. So ideally, we would like our volume equation to be just in terms of height. We would like to find a replacement for radius. So if I want to find a replacement for radius, I'm going to solve for r, so I can remove r and put something else in place of it. So I'm going to solve for r here. R is equal to 10h divided by 30. Therefore, r is equal to h over 3. So I'm now going to update my volume equation. Replace h over 3 in for r. We do want to eventually find the derivative, but right now is not the time. We prefer not to go through a combination of product and chain to get to the derivative. It should be a nice, clean, just power rule. But let's continue cleaning up and merge the variables together, push the coefficients out in front. So pi over 3 times h squared over 9 times h. I can push out the coefficients, pi over 27. I can have that out in front. I can merge the h's together, make it h cubed. Oh, and then we got to be careful with this as well. When they tell us h is 4 centimeters, this is for the end. Not right now. A lot of students want to take that 4 centimeters and start inserting in for all the h's, but then you're losing your h variable, and then you're unable to get to dHdt because all your h's disappeared. So we are going to use this, but only until we have our derivative kind of set our problem in stone a little bit. All right, so now we can move into our derivative. This should be a nice, easy derivative for us to do. V becomes dv dt, h cubed becomes 3h squared dh dt, and the pi over 27 just hangs out in front. Okay, so now we can start putting everything in. We have, sorry, water is poured into a tank at a rate of 10 cubic centimeters per second. What can we assign this to be? The what? Centimeters cubed is volume per second, so dv dt. Yeah, I forgot to add that in. So dv dt is positive 10. It's positive 10 because water is getting poured into the tank. The water is growing inside the tank. So 10 goes in for dv dt. H gets replaced with 4. Now we can use that 4. And then dh dt is the unknown. So we should be able to have everything filled in and have that one last missing variable to look for. You can use your calculator to reduce. Leave pi out of it because we do want to hold on to pi notation at the end of the problem. So I can make this 16 times 9 divided by 27, get that to be a reduced fraction. And then to solve for dH dt, I can just divide this fraction over, which is the same thing as multiplying by its reciprocal. Now, height is only one-dimensional units, right? It's only centimeters. So our final unit of measure should be centimeters per second. If it's area, then it's centimeters squared. If it's volume, then it's centimeters cubed. But everything else is just going to be one-dimensional, whether it's height or radius or base. Okay. And notice that it's important that pi stays in the denominator. We can't have that pi in the numerator. Then it means something else. So in this case, pi has to be in the denominator. Otherwise, we're changing the overall value. So it's not the same with pi being in the denominator versus the numerator. It does make a difference. Okay, number 4. We have a right triangle shown. The angle theta is increasing at a rate of 2 radians per hour. At what rate is the sine length increasing? So anytime you see the word, anytime you see theta involved, you know it's got to be a trig relationship. We got to create a trig equation, either using sine, cosine, or tangent. So that's going to be our starting equation, some trig equation before we find the derivative. Now, everything is here in front of us for us to build our trig equation. We got to decide which trig equation is going to allow us to involve theta, x, and the 5. So we're deciding between sine, cosine, or tangent. So imagine you're sitting here at theta and you're looking out at the x and the 5. Which relationship relationship do we have? Sine, right? So sine is opposite over hypotenuse. So we're going to use that to help us create our equation. So we can use sine of theta is equal to x over 5. Okay. We can find the derivative, but let me rewrite this as sine of theta equals 1/5 x if it helps us to see power rule a little bit better on the right side. So let's find the derivative. Every variable gets impacted by time. So sine of theta becomes what? What's sine's derivative? Cosine. So cosine theta. But this is related rates, so we need to also include what? Times d what? Theta. Yeah, d theta over dt. 1/5 x becomes, but we still have time impacting that variable. So the x disappears, but we still need what? Times the x dt, right? Okay, any questions so far? All right, let's see what we're given here. Angle theta is increasing at a constant rate of 2 radians per hour. What can we assign this to be? D theta dt, okay. It's increasing, so we do want positive. At what rate is the side length increasing? What are we looking for? Dx dt. When x is 4 feet, okay, when x is 4 feet. So we can plug in 2 in for d theta dt, that's great. We're looking for dx dt, that's good, that variable is here. So the only thing that we have to worry about is how do I get rid of that cosine theta? It's not the theta that we're looking for. We're going to find a replacement for this entire cosine of theta. And this is what's different about this related rates for trig is we're going to have to build a second triangle, figure out that ratio, and find a ratio for cosine. So I'm going to draw a second triangle here and see if we can use our information to fill in this moment in time for this triangle. We know this is 5. What do you know about x at this moment in time? X is what? 4, which means that this last missing side must be what? 3. So we're going to use this information to help us find a replacement for cosine theta. Sometimes I see students trying to figure out what theta is, and they have no idea what to do with that theta. We're not looking for theta. We're trying to find cosine of theta. I'm trying to find a ratio for this triangle. So what's cosine of theta equal to? SOHCAHTOA, so cosine theta equals 3/5, yeah, adjacent over hypotenuse. So there's that last missing piece of the puzzle that we need. And now we can fit everything in, right? 3/5 goes here, 2 goes here, and then we can solve for dx dt. So multiply by 5, I get 6, 30 over 5, which is 6. So my dx dt is 6, and the unit is feet per second. I just want to do one more type of problem, and this is a cylinder. A cylinder has a similar formula as cone, but it's a lot easier. Yes, question. Oh, sorry, my bad. That should be hours. I was thinking about the previous problem. Yeah, per hour. Okay, page 11. Okay, so whenever you see a cylinder, even though the formula looks a lot like your cone, sorry, this is page 11. It's an easier problem. Okay, so I see a lot of students wanting to do similar triangles, but there's no need for it. There's no triangle that's gonna appear out of this cylinder. So I want us to just be aware that this is an easier problem because one variable will just go away quickly for us. So a cylinder tank with a radius of 5 centimeters is being filled with water at a rate of 3 cubic centimeters per minute. We know that's dV dt. How fast is the height of the water increasing? We're looking for dH dt. Right. We're asking about the rate of change of the height of the water level, right? And our volume formula is for the water inside the tank, okay? Because that's what's going to interest us. What do you know about the radius of the water level? It's 5, right? Is it going to change from 5? So there's no need to hold on to a variable if it's never changing. The reason why the previous volume formula, we had to hold on to our radius and height because the radius kept changing, the height kept changing. We can't just insert it with a value because as soon as we do, it's going to change to something else. But if we know that our radius is never changing, we can replace that r with a number and then just be done with that variable. Because at the beginning of the problem, the radius is 5. At the end of the problem, the radius is still 5. That's not the case with cones. So that's why cones is a little bit more complicated because we have to figure out how to manage those two variables that's changing. But here, my radius is not changing, so replace radius with 5, and we have a much easier volume equation to find the derivative for because we're just down to 2 variables, v and h. Does that make sense? But Sometimes the cylinder problems may be misleading because sometimes these problems will start giving you information. Like I said, there's a cone problem, and you have all this extraneous information, and so it kind of forces you or kind of misleads you into building all this similar triangle when you don't even need it. And also the formula looks like it, so I think sometimes that can mislead us as well. But if we see a cylinder problem, just replace the radius with a number, and then just find no similar triangle, just find the derivative. So V's derivative is just dv dt. 25 pi is just 25 pi. H just becomes dh dt, and then we're almost near the end. So it should be a much easier process because we can just replace the radius with a number. Okay, so dv dt is 3. And then we can just solve for dh dt. So divide both sides by 25 pi, and then we have our answer. Again, because algebraically pi is in the denominator, we need to leave it there. We can't just move it up to the top. And then what's our unit of measure? Height is a centimeter, centimeter square, centimeters cubed. Just centimeters, right? And then time is minutes. Okay, your homework, page 9 through 12. I'll send out a reminder today, this afternoon. All right, come get your phones.
And the last thing I need in my parents to say for your family, you're not going to listen unless we're all not. Yeah, so I took like 20 seconds. So I started to mention that we're even this children. And I hate to break it. Then I love them so much. Oh, usually 416, 547, and 6. Oh, I was actually studying right now, but very difficult study. And I don't know, I need to let her out. So they said, we're going to call us.